Hello everyone. In this video, I'll be demonstrating how to perform a repeated measures ANOVA in SPSS using a beginner-friendly step-by-step approach. Please stay with me on this channel as I discuss the concept, explore its assumptions, demonstrate a step-by-step practical procedure in SPSS, and interpret the results effectively. My name is Titocan and this is Titocan Max Solutions, a YouTube channel for improving the knowledge of how to do things. Now, let's get started by defining the concept of repeated measures ANOVA. Repeated measures ANOVA, which is also known as within subjects ANOVA, is a statistical method used when you measure the same variable multiple times on the same subject. That is, repeated measures ANOVA is used as a statistical test to compare the means of 3 or more groups when the same subjects are measured under different conditions or at different time points. The purpose of conducting repeated measures ANOVA is to determine if there are statistically significant differences among the repeated measurements on the same subjects. I have produced videos on one-way ANOVA and two-way ANOVA respectively, and you can find them in my YouTube channel at Titocan Max Solutions. It is important that you watch or see those videos first so that you can have a better understanding of these repeated measures ANOVA. There are some assumptions that your data must satisfy before you run the repeated measures ANOVA in order to ensure the test results are valid and reliable. The assumptions are: 1. The dependent variable should be measured at the continuous level as interval or ratio variables. 2. Your independent variable should consist of at least 3 categorical related groups. 3. There must be a related group. That is, the same participants must be used in all conditions or across all time points. 4. The dependent variable should be approximately normally distributed. 5. There should be no significant outliers in the repeated measures. And 6. The assumption of sphericity must be met. That is, the variances of the differences between all combinations of related groups must be equal. Please take note of this assumption and ensure that your data is tenable, because repeated measures ANOVA is susceptible to violating this assumption of sphericity, which consequently can lead to a high rate of committing type 1 error. Now, let's go into SPSS to see the data and perform the analysis. This is the dataset I'll be using for this demonstration, and it has already been loaded into SPSS. If you don't know how to load data into SPSS and define the variable properties, please kindly see my video on Introduction to SPSS Software for Beginner, Part 1 and Part 2 to learn. The link to the videos is given in the description section of this video. Now, let's return to our dataset. This dataset was fictitiously generated to simulate a repeated measures experimental study investigating the effectiveness of a diet plan on weight loss over time. The study was designed to measure whether participants lost weight after being placed on a structured dietary program over an 8-week period. As you can see, the study involved 20 participants, both male and female gender, who were monitored at 3 distinct time points. With week 0 indicates the weight measurement before starting the diet. With week 4 indicates the weight measurement midway through the diet. And with week 8 indicates the weight measurement after completing the diet. Each participant's weight was recorded in kilograms at all time points in the survey. Since the same individuals were measured repeatedly across time, the data structure is suitable for repeated measures ANOVA. But before we proceed to perform the analysis, let's state the hypothesis. The null hypothesis states that there is no significant difference in the average weight of participants across the 3 time points, while the alternative hypothesis states that there is a significant difference in at least 2 of the average weights across the 3 time points. Now, let's perform the repeated measures ANOVA analysis. If you are using SPSS version 24 or earlier version, you'll be able to follow the step-by-step procedure in this demonstration. Go to the menu bar and click on Analyze. From the sub-menu, put your cursor on General Linear Model, and from the drop-down options, click on Repeated Measures to open the Define Factors dialog box. This dialog box is a crucial step in setting up your analysis correctly, because the information you provided here tells SPSS how your data is structured. Now, since our data for this demonstration has to do with the weight of participants measured at different timestamps, I will therefore assign the name time to replace the factor 1 in the within subject factor name box. And since the measurement was done at 3 different time space, then I will enter 3 as an integer in the box for number of levels, and click the Add button to add the factor name and the number of repeated measurements to the box. For the measure name column, I will enter the name weight, since what was measured at different times is weight. These steps tell SPSS that the same subject were measured multiple times and sets up the repeated measures model so that SPSS knows to treat the repeated observations as related and within subject rather than independent. If you fail to provide the correct information in this dialog box, SPSS cannot perform a valid within subject analysis, which is the core of Repeated Measures ANOVA. Now, go ahead and click Define to open the Repeated Measures dialog box. As you can see, the SPSS system has already identified that there are 3 repeated measurements of weight, as you can see in the box at the right for within subject variables for time consisting of 3 placeholders with question marks for the weight measured repeatedly. In this dialog box, your data are in the box at the left. Click on the weight for week 0, hold down the Shift key, and click on the weight for week 8 to select all the weight measured at the different time points. Then, click on this transfer arrow key to move them to the within subject variable box for time to sit in their respective placeholders. If you choose to cross these repeated measures with gender, you can move the gender to the box for between subjects factors. But for this demonstration, I don't intend to cross it with gender because gender has only 2 levels and the post-hoc test will not be produced for it. So I will remove it from the setup. But if your research objectives demand for it, please go ahead to include the gender and you will get some useful results without the post-hoc test. Honestly, this move is optionally based on your research objectives. Now, click on the Model button to open it. In this dialog box, every required selection has been done for us. There is nothing left for us to do. But ensure that the sums of square is type 3. Click Continue to close this dialog box. Click to open the Contrast button. Here too, every required selection has also been done for us. There is also nothing left for us to do. Just click Continue to close this dialog box. Now, click on the Plots button to open the dialog box. In this dialog box, you have only one factor, which is time. Click on the time in the factors box at the left and click on this transfer arrow key to transfer it to the horizontal axis box. Then click on Add button to move the time from the horizontal axis box to the plots box. This will produce a pictorial profile plot of the weight. Click Continue to close the dialog box. Please note that if you are using SPSS version 25 and higher, the settings on this dialog box may differ. Click to open the post-hoc button. In this dialog box, there is nothing here for us to do at all since there is no variable in the factors box. This is so because we didn't cross the analysis with any independent variable. I couldn't cross it with gender, which is the only independent variable that I had, because gender has only 2 levels and the post-hoc test will not be produced for it because post-hoc test requires at least 3 levels to operate the required comparison. So be advised that your independent variable must have at least 3 levels. Since there is nothing for us to do here, click Continue to close this dialog box. In the Save dialog box, the options here are at your discretion to choose. So you can check any box as you require. But for this demonstration, I don't intend to do anything here. So I will just click Continue to close this dialog box. Finally, click on the Options button to open the dialog box. In this dialog box, click on Time from the Factors and Factor Interactions box at the left and click on this transfer arrow key to transfer it to Display Mix for box at the right. Then check the box for Compare Me Effect and thereafter click on the button for Confidence Interval Adjustment and select Befferoni from the drop-down options. Now, in the Display section, check the box for descriptive statistics and estimates of effect size. Ensure that the significance level is 0.05. Click Continue to close this dialog box. Like this, we have successfully completed the setup to perform the repeated measures ANOVA. So go ahead and click OK for the SPSS system to process the setup and produce the results in the output window. Now, as you can see, the results have been produced. There are several key result tables here that are essential for meaningful discussion and interpretation. But I will guide you through to discuss the most important ones only. Proceed to the descriptive statistics table. This table provides a clear picture of how participants' weight changed over the course of the diet program at different timestamps. That is, it shows you the overall pattern or trend of your data, whether the weights are increasing or decreasing. As you can see, for each timestamp or for each time point, there are 20 cases. Suffice to me that the entire people participated in the dietary plan. There was no missing data. At the beginning of the study, labeled as week 0, the average weight of the 20 participants was 80.430 kilograms, with a standard deviation of 8.4865. This indicates that before the intervention began, the group's average weight was around 80 kilograms, with individual weights showing a moderate variability. By week 4, after 1 month on the diet plan, the average weight had decreased to 78.310 kilograms. This reflects a reduction of approximately 2.12 kilograms from the starting point. The standard deviation at this point is 8.4312, which is similar to that of week 0, suggesting that the variability in participants' weight did not change much. That is, the participants were responding to the program in relatively similar ways 1 month after. At the final time point, week 8, the mean weight further dropped to 75.270 kilograms, marking a total average reduction of about 5.16 kilograms from the baseline. The standard deviation here was 8.7768, which is slightly higher than the previous weeks. This increase suggests that while most participants continue to lose weight, some may have lost more than others, indicating a slight increase in variability in the weight loss outcomes as the program progressed. Generally, the results in this table show a consistent downward trend in weight over time, showing that the diet program had a positive impact on participants' weight. However, while these descriptive values provide an overview of how the average and spread of the data have changed, they do not yet confirm whether the changes observed are statistically significant. To draw any firm conclusions about the effectiveness of the diet program, we must examine the inferential statistics, which will test whether the differences in weight across the 3 time points are significant beyond random variation. The inferential statistics are in the table for test of within subjects effect. But before you go there, you need to be sure that the assumption of sphericity is met. That is, the variances of the differences between all combinations of related groups is equal, because violating sphericity can inflate type 1 error rates. So, let's proceed to Markley's test of sphericity table. This is the Markley's test of sphericity table. This table provides the test results of the important assumptions of sphericity, which tests whether the variances of the differences between all combinations of related groups is equal. Otherwise, the assumption number 6 in this video is violated, and that will mean there is no accuracy in the analysis results because such a violation inflates type 1 error. So in this table, you will have to concentrate on the p-value column designated as SIG. Now, if the p-value is greater than 0.05, then the assumption of sphericity is met, and you are advised to use the standard ANOVA result, which is the rho for sphericity assumed in the test of within subjects effects table. But if the p-value is less than 0.05, then the assumption of sphericity is violated, and only under this condition you are advised to use Greenhouse-Geyser or Hayes-Fett results as corrections to adjust the degrees of freedom. You will understand this information better when we get to the next table. However, as you can see from this table, the p-value designated as SIG is 0.102, which is greater than 0.05, indicating that the assumption of sphericity is met, and the variances of the differences between all combination of related group is equal. Now, proceed to the next table, which is the test of within subjects effect. This is the main inferential statistics table of the repeated measures ANOVA and is the most important table. Information on this table confirms whether the changes observed in the descriptive statistics table are statistically significant, but in discussing this table, you are strongly advised to only interpret or use the appropriate rule for time based on the Markley's test of sphericity as we have seen in the table above. So, if the assumption of sphericity is met, you will have to interpret the sphericity assumed rule for time. Otherwise, you will have to use the rule for greenhouse gaser or High-use if the assumption of sphericity is violated. But since the assumption of sphericity is met, showing that the variances of the differences between all combinations of related groups is equal, as we have seen in the table of Markley's test of sphericity, I will just go ahead to use and interpret results information along the rule of sphericity assumed. In this table, you should concentrate only on the three last columns, that is the F statistics column, the p-value column designated as SIG, and the partial eta square column for effect size. As you can see in this table, the rule of time for sphericity assumed has F statistics of 142.398, p-value of 0.000, and the partial eta square of 0.882. The F value of 142.398 indicates a very strong statistical difference in the mean values of the dependent variable measured across the different time points. With a p-value of 0.000, which is well below the standard threshold of 0.05, we can confidently reject the null hypothesis because at least there are changes over time. This means that the repeated measures of the weight at different weeks significantly differ, and this difference is unlikely to have occurred by chance. Furthermore, the partial eta squared value of 0.882 suggests an exceptionally large effect size. In statistical terms, this means that approximately 88.2% of the total variance in the dependent variable can be attributed to the effect of time changes, which is a very substantial proportion. This shows that the treatment has a powerful and consistent impact on the participants' weight across time. Overall, this result provides strong evidence that the measured variable significantly changed across the repeated observations, and the change is both statistically significant and practically meaningful. The next table is a test of within subjects contrast. Discussing this table of results is, however, optional but helpful because this table breaks down the results of within subjects effect table further by helping to understand the shape of the trend of changes over time. So this table is only useful if you intend to describe the pattern of change, such as if the change is steady decline or curved drop. That is, the contrast analysis breaks the time effect down into linear and quadratic trends to explore whether the changes are consistent over time or whether they follow a more complex pattern. Starting with the linear time contrast, the value for type 3 sums of square is 266.256 with 1 degrees of freedom. The corresponding mean square is also 266.256, producing an F statistics of 202.728, which is highly significant with a p-value of 0.000, which is less than 0.05. Most importantly, the partial eta squared value is 0.914, which indicates that 91.4% of the variance in the repeated measure is explained by a linear trend over time. This suggests a strong and consistent downward pattern or a steady progressive decrease in the dependent weight variable from the beginning to the end of the observed period. In practical terms, this tells us that participants are showing consistent weight loss from week to week, and the change is both statistically and practically significant. On the other hand, the quadratic time component shows a type 3 sums of squares of 2.821 with 1 degrees of freedom and a mean squares of 2.821. The resulting F statistics is 4.896, which is statistically significant at the 0.039 level because the p-value is less than 0.05. The partial eta squared for the quadratic effect is 0.205, meaning about 20.5% of the variance is explained by a curved or nonlinear trend. This indicates that while the overall trend is largely linear, there is also a modest curvature in the pattern, possibly suggesting that the rate of weight loss is not exactly the same at all intervals. For instance, participants may have lost weight more rapidly at the beginning of the program, with the rate of weight loss slowing slightly over time, or vice versa. But generally, looking at this table, these results highlight two key findings. First, there is a dominant and strong linear effect, meaning that the intervention or condition is yielding steady, continuous changes. And second, there is a minor but notable quadratic trend, hinting at some variation in how that change unfolds across time points. This dual interpretation offers a richer understanding of the time-based effects, emphasizing both consistency and subtle shift in the response to the intervention. The next table is a test of between subjects effect. This table should be discussed if you include an independent variable as between subject factor, which I didn't do in this demonstration because my dataset didn't have a factor that has at least 3 levels. Such an inclusion will test if different groups respond differently across time. Most importantly, results in this table are basically useful when exploring interaction effect or subgroup analysis. So I will leave this option for you to try on your own. Now, the last table to be discussed in this tutorial is the table of pairwise comparison. This table is necessary for a post-hoc test. If the main effect is significant, these comparisons will tell you which time point differs significantly from one another among the time points. That is, it pinpoints where exactly the change occurs. So, in this table, there are 2 columns to consider. That is the mean difference column and the p-value column designated as SIG. If the mean difference for each comparison carries asterisk and their corresponding p-value is less than 0.05, then it indicates the source of the significant difference, pinpointing exactly where the changes occurred. If the p-value is greater than 0.05, there will be no asterisk in the mean difference value. So, as you can see in this table, all the mean difference between pairs of time points are marked with an asterisk, indicating that these differences are statistically significant. Moreover, each of these comparisons has a p-value of 0.000, which is less than 0.05, which strongly suggests that the differences are not due to chance. Specifically, a p-value of 0.000, which is typically interpreted as p-value less than 0.001, means there is a less than 0.1% probability that the observed differences occurred randomly. This level of significance provides compelling evidence that the weight of participants changed significantly between each of the observed time points. What this means in practical terms is that participants did not just show a general trend of weight loss over time, they experienced distinct and statistically significant reductions in weight at each stage of the intervention. For example, the difference between week 0 and week 4, week 0 and week 8, and between week 4 and week 0, week 4 and week 8, and between week 8 and week 0, week 8 and week 4 were all significant. The asterisks in their mean difference reinforce this conclusion by highlighting that each pairwise comparison shows a meaningful change. Altogether, these results from the pairwise comparison table strengthen the overall findings of the repeated measures ANOVA by confirming that each stage of the program led to a measurable progress, providing actionable evidence that the intervention is effective at multiple stages, not just over time as a whole, but at each point in the timeline. This level of detailed insight is valuable for both evaluation and future planning. Finally, let's take a look at the plot. This is the Repeated Measures ANOVA plot. It provides a visual representation of how the dependent variable changes over the different time points. It is an important supplement to the statistical output because it allows for immediate intuitive understanding of the data trends. As you can see here, the plot reveals a consistent downward trend in participants' weight across the 3 measured time points. The average weight visibly decreases from week 0 to week 4 and continues to decline through week 8, suggesting that the intervention or program in place is effective over time. That is how to perform the Repeated Measures ANOVA in SPSS and interpret the results. But right now, we have come to the end of this video, and I hope you'll be able to replicate the procedure to run the analysis on your own dataset and interpret the results. But wait, if you find this tutorial helpful, click the like button, subscribe to Titocan Solutions for more data-driven insights, and hit the notification bell so you never miss out on our latest tutorials. Do you have questions? Drop them in the comment section. Let's keep the learning going. And hey, if you are working on a real-world project and you need guidance, let's talk, because learning never stops. Thanks for watching, and thanks for subscribing to Titocan Solutions, a YouTube channel for improving the knowledge of how to do things. See you in my next video. Bye.